And welcome to page 3. This is your acid-base page. We're going to start with part A, which is just those pK values that you were asked to memorize. I did a favor for you, put them in order of most to least acidic. That may not happen in the future, just a heads up there. So we start on the left. Hydrochloric acid is a very strong acid, has a pK of -7. Hydronium is 0. The pK of this proton in acetic acid is 5. Ammonium is 10, and just keep in mind that that positive charge is actually on the nitrogen. The pK of water is about 16. The pK of acetone, which is an alpha proton, one where you have a hydrogen on the carbon next to a carbonyl, has a pK of 19, and you get a little hint of that down below. Ammonia, which is where nitrogen has 3 bonds on a lone pair, is a pK of 35. And finally, methane has a pK of 50. That proton's pretty much not going anywhere for a while. Next, we're going to rank the molecules in terms of acidity. 1 is the most acidic, and there's no ties. So first of all, let's fill in acetic acid's pKa is 5. We saw that from above. And a low pKa means a low affinity for its proton, and that means a stronger acid. It's all relative. So this is going to be the strongest acid here, number 1. Next, we have pentanedione, which is given a pK of 9, so that is a pK of 2. And just a little heads up, it actually is the proton in between the 2 carbonyls. That'll be something useful for you more in Chem 8b. We then see next that the phenol proton here has a pK of 10. It's number 3. And then acetone is going to be number 4. Next part, we want to think a little more detailed about how we're going to approach these types of problems, meaning we have to think in those steps. So step 1, we're going to assign each compound to a pKa family. So I'm going to give it an approximate pKa. This first one is an alcohol here. It has a pKa, it has a pKa like, or it is like water. It's in water's pKa family, so instead of an HOH, it's COH. This guy's going to have a pK of about 16. And since we have this fluorine group, this is an electron withdrawing group, or rather it's an electronegative atom. It's the same deal. It's going to be pulling electrons away from the conjugate base, and I'll just show at least one of these conjugate bases. The deal is whenever the acid loses that proton, we're asking the question, how stable is that negative charge? And if we have an electronegative fluorine pulling away electrons by electronegativity, that is going to make for a more stable conjugate base, and this is relative to water. So H, the hydrogen in water, is not going to help stabilize the conjugate base. So anyway, what I'm getting at, this has a pK less than 16 because of that electronegative fluorine. We then move on to the next compound. Notice I haven't really started ranking yet. This guy here has a pK of 5, right? And so we know that, and there's no reference or nothing to compare it to because that's just the pKa standard. We see another example of an alcohol here, so we'll put this back on the blue team. This has an electronegative atom, but bromine is not quite as electronegative as fluorine, so it's less of a pull. So it's still going to have a pK less than 16, but I would go ahead and just say, in comparison to the fluorine molecule, not quite as much. So fluorine is, the fluoroalcohol has a pK much less than 16. The one with just 1 bromine has less than 16, and then we'll go on to the next ones here. All right, so we're going to categorize again. We're going to put this on the green team. This has a pK of about 5. We have 2 electronegative fluorine atoms that pull that negative charge away. So this is going to have a pK less than 5. Now, I'm not going to say much less than 5, even though there's 2 fluorines, because I'm only comparing 2 carboxylic acids. So those are the only 2 of these 6 compounds that are in that pKa family of 5. And then compound number something 5, we see this is like HOH, or like water. This has a pK of about 16, and because this carbon stuff all donates in by the inductive effect, we could say that it's a little bit greater than 16, but it's definitely going to be less acidic than the bromo and fluoro alcohols. And finally, last but not least, we have the hydrobromic acid, which has a pK of -7. It is like HCl. Okay, there's no one else in this set 2 with a similar pKa family, so we don't need a less than or greater than to know that this is going to be the most acidic. Next, we go to the green team, which is a pKa of around 5, and we see that this is going to be next because it's more acidic than acetic acid. This is going to be number 3. What we have left are the 3 different alcohols, so we've simplified our problem. We go for the most acidic of the alcohols, which is where we have the most electronegative atom being fluorine, so that's number 4. The one with the bromine is number 5, and the one without electronegative atoms is going to be dead last, number 6. So that's how you rank acids. Again, step 1, organized by pKa family, and I did that with various colors. And then within each pKa family, you want to identify what types of groups you have. Electronegative atoms increase acidity, and alkyl groups inductively donate and decrease acidity. So let's move on to the nice big acid-base problem. Lots of good stuff going on here. We're going to identify which one's the acid and base. Going to use some curved arrows to explain how the protons get moved around, draw those products, label them as a conjugate acid or base, and predict the direction of equilibrium. So one at a time, we're going to identify pKa families wherever we can. This ammonium group with where nitrogen has 4 bonds and a positive charge is like NH4, or again, like ammonium. So this has a pKa of about 10. So you can identify this by itself as a proton donor. It just has extra protons. And I hope that you identify hydroxide as a base. This is an acid. And so then we're going to start our arrows at the base, the lone pair on oxygen, and we're going to end, weird, what just happened? We're going to start at the oxygen and end at the hydrogen. We're going to be making a new oxygen-hydrogen bond, and then the 2 electrons between nitrogen and hydrogen go on to the nitrogen. That's the whole point of why this is an acid, because it would really like to lose a proton so that it can be neutral. What we get there is, instead of NaOH, we get HOH, or water. Now keep in mind that sodium here, sodium, what I want to do. This guy, he's a spectator ion. There's no covalent bond between the oxygen and the sodium. There's no line there that we need to account for, so we don't need to explain what happens to the sodium. We kind of draw it off to the side, and actually if you left out sodium from your products, that's fine. Same thing with chlorine. Chlorine's a spectator ion. It doesn't actually participate in the reaction, and you can see that based on the arrows here. You can see that there's no arrows to or from a chlorine. Anywho's, so what we have, water, is what the base looks like with an extra proton. So this is the conjugate acid. The other product is still a methyl group connected to a nitrogen that now has 2 hydrogens. This is what the acid looks like without its proton. This is the conjugate base. So this could act as a base, and the reverse reaction, that lone pair, could go over and, did this freeze? The lone pair, I'm just going to keep going. The lone pair could go back and pick up that proton. Oh, good. Great. All right, so then we're going to add the pKa of the conjugate acid, which I just said was water. This has a pKa of 16. So these are the 2 numbers that you can compare to determine the direction of the equilibrium. The acid on the left side of the equation and the acid on the right side of the equation. I do not care that the pKa of this is 35, because that is not the conjugate acid. The question is, who cares about that proton more? The ammonium group on the left, which has a pKa of 10, or water on the right, which has a pKa of 16? And the answer is water wants that proton more, because a higher pKa means a higher affinity for the proton. So again, water wants that proton more, and that's why the equilibrium is favored to the right. Next, we have a reaction between acetic acid and purity. We identify acetic acid having a pKa of 5. We don't have a good pKa for pyridine, meaning, the nitrogen doesn't have an extra hydrogen, so we wouldn't assign that a pKa of 35. All that we have, the only hydrogens that we have are carbon-hydrogen bonds. So I guess if you had to assign a pKa of this guy, it would probably be about 50, because it's like your CH4 molecule where it has just carbon-hydrogen bonds. So from that, we identify acetic acid as the acid. No big surprise there. And pyridine as the base. So we're going to start the electrons at the lone pair on the base. We're going to end at the hydrogen. Remember, it's this hydrogen connected to the oxygen as opposed to one of the hydrogens over here. Much easier to break an oxygen-hydrogen bond. It's much more polar. These 2 electrons then get dumped onto the oxygen. We'll draw our product over here from that. So it's just acetic acid without a proton, making sure we add a negative charge. And then we can identify this as the conjugate base, because this is what the acid looked like without its proton. The conjugate acid then would be what the base looks like with an extra proton. This guy here, positive charge on the nitrogen. So notice that my starting materials are neutral, so my products need to be neutral as well. And once again, this is the conjugate acid. We have some pKa labels to add. We want to add that this has a pKa of about 10 because it's like NH4 plus or ammonium, and you can identify that because the nitrogen has a positive charge and it has 4 bonds, including one to a hydrogen. So the 2 acids that we're comparing are the ones on either side of the equation. We're comparing acetic acid versus ammonium. And again, we see that the right side of the equation has a higher pKa. So the equilibrium is going to be favored strongly to the right. It's actually 10 to the 5th to the right. That's kind of a side note, but that's how we do the acid-base stuff. Last little thing I'm remembering, I sort of promised, if you had over here sodium chloride as a byproduct, or if you wrote sodium chloride separately like that, that's fine too. But again, those are just spectator ions. These are spectators. They're just along for the ride. They don't participate in bond breaking or forming, so they're not actually labeled as a conjugate acid or a conjugate base. So I hope that was helpful. I'll see you on page 4.